we will continue our discussion with acid-base reactions. First of all, let's discuss a little bit what an acid and a base are. An acid is that kind of substance that when it's placed in water and it dissolves, it produces H plus ion. These are called hydrogen ions, they're called hydronium ions, but it's H plus. For right now, we will just call them H plus ions. A base, on the other hand, is that kind of substance that when we place it in water, it gives us hydroxide ions, OH minus ions. Here is a reaction of an acid and a base. If I put HCl in water, it will split into H plus and Cl minus. If I put NaOH in water, it will split into Na plus and OH minus. So it's a base because it produces OH minus. HCl is an acid because it produces H plus ions when dissolved in water. When we react an acid and a base together, the subsequent reaction is called a neutralization reaction because the acid and the base neutralize each other, and if they are mixed in the appropriate amounts, in proportionate amounts, they will produce a salt and water. And that's why it's neutralized, right? It's a neutralization reaction because I start out with an acid and a base, which can be caustic, and then I end up with water and just a salt, which aren't really harmless products. And that's why we say the acid neutralizes the base or vice versa. So that's a reaction between an acid and a base. Here's the problem for you to try. Milk of magnesia is made of a suspension solution of magnesium hydroxide and water. Now it looks milky white because MgOH2, so magnesium hydroxide, is insoluble in water. Review the flow chart to convince yourself that that's true. Now, when we pour acid into milk of magnesia, or MgOH2, which is a base because it can produce OH minus in solution, it dissolves the solid MgOH2, and we have a neutralization reaction that occurs, giving me a clear solution. You can see that the milky white is gone, and the milky white is due to the undissolved MgOH2. Write and balance the molecular equation first between the base and HCl, the acid. Write the neutralization reaction. Then write the complete ionic and net ionic equations for this reaction. The next reaction that we're going to talk about is oxidation reduction. This occurs many times in nature. Oxidation reduction reactions are called redox for short. So reduction and oxidation redox reactions. In these reactions, what is happening is that we exchange electrons. One reactant loses them and the other gains. And of course, the number of electrons that is exchanged has to be the same. If one reactant is losing 2 electrons, the other one better be gaining 2. Okay, we don't lose electrons either, just like we don't lose or create matter. The loss of electrons is oxidation, and the gain of electrons is reduction. So reduction and oxidation are opposite processes that occur simultaneously, but oxidation, you lose electrons. Losing electrons meaning you're losing negative charge, so the element is becoming more positive. Reduction is the opposite. You're becoming more negative because you're gaining electrons and therefore you're gaining negative charge. Here's an example. So if I have an aqueous solution of copper sulfate, for example, and I put a strip of zinc in that solution, what happens is that I have an exchange here. The copper, which is copper 2 plus in solution, gains 2 electrons from the zinc and gets deposited as an element, just copper 0, on the surface of the zinc strip, whereas the zinc ions then, losing those electrons, they're not held on the surface of the strip anymore, but come out and enter the solution as zinc 2 plus. And so you have this exchange of the copper for the zinc. Zinc comes in solution, copper takes its place, and over time you will see the buildup of copper atoms, right? Copper now, because it gained 2 electrons, is copper 0. It gains those electrons and it gets deposited on the surface, whereas the zinc gets into the solution. You have a change in color of the solution and the change in color of the metal on the surface there. When we do a redox reaction, we talk about oxidation numbers. Remember that oxidation, so if something is being oxidized, is losing electrons, whereas reduction is gaining electrons. An easy way to remember that is oil rig. Oxidation is loss, reduction is gain. Many students use this oil rig. And because oxidation is loss of electrons, the atom is becoming more positive, and the opposite is true for reduction. Now, the oxidation number of any element as it appears in its elemental form, so as it appears in the periodic table, is 0. So if the element is alone without being combined with another element, that oxidation number is 0. Then the oxidation numbers in any other chemical species must sum to the overall charge on that species. So if I have a molecule that is neutral, the oxidation numbers of all of the elements in that make up the molecule must add up to 0. If I have a polyatomic ion that has a charge, all of the oxidation numbers have to add up to the charge on that particular polyatomic ion. If I have the oxidation number of a monoatomic ion, right, an ion that it's got one element, not many, that is equal to the charge of the ion, the oxidation number. So let's take a look at the reaction that was happening in the previous slide. We had zinc metal on the surface and then copper 2 plus ions in the solution. Zinc, since it is not combined with anything else and it appears in its elemental form as it is in the periodic table, it has an oxidation number of 0. So zinc is 0. However, copper is 2 plus. That means that it's a monoatomic ion. The oxidation number for that is equal to the charge on the ion. So since the charge is 2 plus, the oxidation number of copper is 2 plus. Now, what is happening is that zinc is coming out in solution as a 2 plus ion, and copper is being deposited as copper solid, as it appears in the periodic table in its elemental form. So copper is going from plus 2 to 0. Since it's becoming less positive, right, from +2 to 0, 0 is less positive than +2. You're moving in from basically +2, if we write a little number line, +2 will be on the right-hand side, 0 will be here, so you're moving to the left, right, to the left of the number line. Then that means that copper is becoming reduced because it's becoming more negative. Zinc starts at 0 and it ends up at +2, so it's becoming more positive. 0 + 1 + 2, that means that it's becoming more positive, which means that it's being oxidized. Oxidation is loss. It's losing electrons. Let's look at this reaction here. I have hydrogen gas and fluorine gas giving me hydrogen fluoride. Well, hydrogen gas, it appears like it does in the periodic table in its elemental form. Even though it's a diatomic molecule, it's still its elemental form, and it has an oxidation number of 0. The same thing can be said for fluorine, so its oxidation number here is 0. However, now that they're combined in a molecule, what is the charge on the fluorine? It's -1. What about the hydrogen? Well, it has to be +1 because I'm pairing a -1 and a +1 ion to give me a 0 overall charge. Now, the oxidation number is not the same as the charge, obviously, because this is a molecule. However, the oxidation numbers in a chemical species must sum to 0 for a molecule. Since that HF is a molecule, the oxidation numbers of both hydrogen and fluorine must add up to 0. And +1 - 1 gives me 0. Not only that, but the charges on both sides have to be equal, right? If I have a 2+ on this side, I have a 2+ on that side. That is equal. Here the overall charge is 0, and on this side is also 0. Here's some rules on how to assign oxidation number. Fluorine will always have an oxidation number of -1, unless it is alone as F2, and then it will have a 0, because that's its elemental form. There are no exceptions to this rule. Group 1A or 2A metals will have an oxidation number of +1 or +2, respectively. So group 1A will have +1, group 2A will have 2+. Hydrogen will have a +1 unless it's combined with a group 1A or 2A metals to form a metal hydride, like lithium hydride and calcium hydride. In this case, the oxidation number of hydrogen is -1 in both examples. Oxygen has a -2 oxidation number, unless it's combined with something that is higher on this list, that it necessitates that it has a different oxidation number. Otherwise, it will have a -2. Here's some examples of exceptions: H2O2 and KO2. For H2O2, the oxidation number is -1, and for KO2 is -1/2. -1/2, you have 2 oxygens, which make the total oxidation number, or total negative oxidation number, as -1. Potassium has a +1 oxidation number, so +1 - 1 gives you an overall sum of 0. And then group 7A other than fluorine, so chlorine, bromine, iodine, have a -1, but if it's combined with anything higher on this list, then it can have a different oxidation number. So ClF, BrO4-, IO3-. The oxidation numbers of chlorine, bromine, and iodine in these 3 molecules are +1, +7, and +5, respectively. Okay. Fluorine, however, will always have an oxidation state of -1 when it is part of a compound. When it isn't, it has an oxidation number of 0. Let's take a look at how to work on oxidation numbers, determining oxidation numbers. Here's my molecule, right? And you can write this out similarly, or you can find your own way to write these out. From the table, we know that potassium, being group 1, will always have an oxidation number of +1, and it will contribute that +1 to the charge. When we go to the next one, we're not quite sure, so we'll skip that because it's not in the table. We'll skip it for right now, and let's go to oxygen, which we said has a -2 oxidation number. However, because I have 4 of those, its total contribution to charge is 4 times -2, -8. Okay, so I have a +1 on this side and a -8 on this side. That means that since this molecule is neutral, I would have to have a +8 to counteract that -8. And to get a +8, manganese has to be +7. So +7 +1 gives you +8, -8 will give you 0, which is the overall charge of this molecule. And sure enough, here's the manganese +7 charge. Here's a sample problem for you to try. Determine the oxidation number of each atom in the following compounds or ions. I am doing the first one for you for SO2. From the table that we looked at, oxygen will have a 2- oxidation number, but you have 2 of those, and therefore the total contribution to the charge of oxygen will be 2 times 2 -4. The lone atom will have to carry all the positive overall, you'd have to contribute a positive oxidation number to get an overall charge of 0. If this has a -4, this has to be a +4, so it has to have a +4 oxidation number to be able to counteract that -4 charge, contribution to the charge from the oxygen. Now you try B, C, and D on your own. We can have several types of redox reactions, but redox reactions are those reactions where we have a change in oxidation state from reactants to products. The first redox reaction type is single displacement reaction, not to be confused with double displacement reaction. In a single displacement reaction, we have an element and a compound as starting material, and this element is replacing another element in this compound. It's taking its place. So it's kicking out copper to singly displace it. There is no double displacement here because zinc doesn't have an anion to where I can swap anions. Remember that for double displacement, we have to have both starting compounds, both reactants, as ionic compounds. Here we have an element and an ionic compound. So the element kicks out the existing positive ion from CuSO4 to take its place and its charge as well. So zinc starts out at 0, but it ends up as +2. Oxygen has a 2- charge. There's 4 of those. 2- times 4 gives you a -8. Copper has a +2. +2, you have only 1 of those, so it has a total contribution of +2. Now, to go from +2 to neutralize -8, you need to have +6 to be able to get +8 -8. That means that sulfur has an oxidation number of +6. The same thing is calculated here, but instead of copper, we have zinc. And here zinc goes from 0 to +2, is becoming more positive, which means that it's losing electrons. Copper goes from +2 to 0, which means it's gaining electrons because it's becoming more negative and it's being reduced. A combination reaction is the combination of reactants, just what it sounds, combination of reactants to form one single product. Here's an example. I have nitrogen plus hydrogen to give me ammonia. Nitrogen has a 0 charge, hydrogen has a 0 charge. Here, hydrogen has a +1, but you have 3 of those, so +3 total. Nitrogen has to have a -3 to counteract the hydrogen. Okay, so we have two species combining together, two reactants combining to give one single product. That's a combination reaction. A decomposition reaction is when you start with one reactant and it breaks down to give you 2 or more products, just like here. So sodium hydride breaking down to give you sodium solid and hydrogen gas. A combustion reaction is a reaction in which we have a substance that is burning in the presence of oxygen to give you CO2 and H2O. So anytime you see oxygen as a reactant, that would be a combustion reaction. And if it produces CO2 and H2O, it's a combustion reaction that is complete. You can work through the oxidation numbers of these two yourself to make sure that you agree with the values that are written in here. Here's a sample problem. Determine whether each of these 4 reactions here represents a combination reaction, a decomposition reaction, or combustion reaction. You can choose multiple ones, so check all that apply in your answer. Here's another sample problem just like the one that you did, just to give you a little more practice. Figure out what type of reactions these are. Check all that apply because you might have multiple of one. Last bit of chapter 10 that we're going to talk about is introduce energy in form of heat when we talk about chemical reactions. Some chemical reactions can require heat to occur, and some give off heat when they occur. Those chemical reactions that require heat to be able to occur are endothermic reactions. Endo meaning they need heat. For an endothermic process, when the heat must be added, we add the heat as a reactant, so to the left-hand side. Those reactions that release heat when they occur are exothermic. They produce heat, and this should be exothermic. Those, when they release heat, it will appear on the right-hand side as a product along with the other products. And we treat it, so in an exothermic reaction, we treat it as a product that is formed after the reaction occurs. Whereas in an endothermic process, it appears as another reactant on the left-hand side. Let's kind of take a look, basically a review of the chemical reactions here. So if an aqueous reactant is combined, do I have a precipitate forming? If I do, then it's a precipitation reaction. If no, then is one of the reactants an acid? Is one of the products water? If yes, then it's an acid-base reaction. If no, then do oxidation numbers of these elements change? If they do, then it's a redox reaction. If you have an acid-base reaction, if the products include water and an aqueous salt, if they do, then it's an acid-base neutralization reaction. If no, so you don't have H2O or an aqueous salt as a product, is one of the products a gas? If yes, then you have a gas-producing acid-base reaction, not a neutralization reaction. Then, if you have a redox reaction, does one metal replace another in the ionic compound? If it's yes, then you have a single displacement reaction. If no, do you have a single product that formed from two or more reactants? If yes, it's a combination reaction. If no, do you have a single reactant from two or more products? If yes, it's a decomposition reaction. If no, then you look at the reactants, and if you have oxygen as one of the reactants, and the only products are CO2 and H2O, then you have a combustion reaction.